Alright, on this video we're going to talk about carboxylic acid and amine aqueous equilibria. And we'll start with carboxylic acids. And there are many examples of them. The first one is the simplest one, which is formic acid. Oops. The next one is acetic acid, where you have a CH3 group, which is also called a methyl group, methyl. Then you can have 3 carbons, and that's called propionic acid. So you have CH3 connected to CH2, which is connected to the C double bond O OH group, called propionic. And one more would be butyric acid, which has 4 carbons, 1, 2, 3, 4. Fourth carbon is part of the C double bond OOH group. And in general, oh wait a minute, let me write down butyric, butyric acid. And in general, we can just use the letter R to indicate the carbon chain connected to the carboxylic acid group. So you recognize that you've got an organic acid when it contains the COOH group, and there's that double bond on one of the carbons. So the Ka values for formic acid, Ka 1.8, 10 to the minus 4, acetic acid 1.8, 10 to the minus 5, propionic acid 1.3, 10 to the minus 5, butyric acid 1.4, 10 to the minus 5. So they're all, with the exception of formic acid, they're around 10 to the minus 5 in magnitude. Formic acid is a little bit of a stronger acid there. You get more dissociation, which is indicated by the magnitude of the number 10 to the minus 4. So, make a few more comments with regard to structure. Let me look at propionic acid. The other name for it is propanoic acid. And the structure is what I wrote before, CH3, CH2, C double bond O, OH. Another way to write this out would be you just write out the hydrogens on the carbons. So each carbon is going to have 4 bonds. So that's written out in the detail. And also you've got here lone pair electrons. This is the first time I'm putting them in. But if you did the count, you would see that the oxygen has 8, so it'd be 2, 4, 6, 8 electrons around it. And this oxygen would be 2, 4, 6, 8 as well. So every atom there has 8, with the exception of hydrogen, 2, 4, 6, 8, and 2, 4, 6, 8. Alright, and then another way to write this is to take this whole group and see that that is equal to C3H5. So another way to write this would be C2H5. C2H5, and then connected to the carboxylic acid group, and put the electrons in like that. Alright, so then moving on, pick one of these organic acids and look at the hydrolysis of it in hydrolysis of water by propionic acid. And I guess I can write it as C2H5, C double bond O, OH. And then in the presence of water, so here the proton, the hydrogen ion, breaks off from the carboxylic acid and interacts with the water to form hydronium. And so the product of the reaction is going to be C2H5 and connected to C double bond O, O, and the hydrogen breaks away without any electrons, and so that's going to leave it 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, which gives it an overall negative charge because it's taken both electrons from the bond, so one more, the extra one comes from the proton, and then, or from the hydrogen atom I should say, and then you have hydronium, H3O+. So let's say that we have a 0.1 molar solution of propionic acid. Going to have an ice table here. 0.10 molar to start with, and we have 0 and 0, and then when the system goes to equilibrium it will be 0.10 minus X, X, and X. We can use 1.3 times 10 to the minus 5 as the value of Ka for propionic acid. That'll be equal to X squared divided by 0.10 minus X. Do the test. 0.1 divided by 1.3, 10 to the minus 5 is greater than 100. So it's appropriate here to drop that X. Makes it a lot easier. X will be equal to the H3O plus concentration, or the H plus concentration, which is the square root of 0.10 times 1.3, 10 to the minus 5, and that will be equal to 1.14, 10 to the minus 3. Alright, let me squeeze down in the bottom. Actually, I can probably move this up a little bit. Give it a little bit more space. So then the next part would be to calculate the pH, negative log of the H plus, or the H3O plus concentration. The pH will be equal to 2.94. So this would be the pH for the propionic acid. Next we have the amines. And the amines are basic compounds, and they are going to be analogous to NH3. So we could write out a few of those just to compare and contrast. We have NH3, which is our prototype. Then we could look at CH3, NH2, and CH3, 2NH, and then CH3, 3N. So 4 compounds there. The first one is called ammonia. Second one is methylamine. Third one is dimethylamine. And the third one is trimethylamine. AMINE. All one word. So if we wrote out the structures, we've got NH3, and remember there's going to be 8 electrons around the central atom here, which means that the nitrogen also has this lone pair of electrons, which are very important to the acid-base chemistry. Methylamine is similar, except instead of one of the hydrogens, you have that CH3 group. So you have a CH3. Otherwise it's the same, and the chemical reaction with water is going to be the same, and with acids as well. Dimethylamine is going to have 2 methyl groups, 1 hydrogen, and trimethylamine has 3. Kb values 1.8, 10 to the minus 5, which is the same as the Ka value for acetic acid. If you remember, that's just a coincidence. Kb for methylamine 4.3, 10 to the minus 4. For dimethylamine 5.9, 10 to the minus 4. And trimethylamine 6.30 times 10 to the minus 5. If we looked in detail at methylamine, which we can write as CH3, we could also write out the methyl group structure in detail. This is the methyl or CH3 group, and notice carbon has 8 electrons around the central atom here, and nitrogen, whoops, forgot to put in the lone pairs, right? So nitrogen has 8 electrons around the central atom. So that would be the methyl group, and the compound would be called methylamine. Now the chemistry is going to be similar to ammonia, and we can first start with ammonia and write out NH3 plus H2O, and here water acts as the acid, donates NH plus, so that NH4, which has an overall positive charge, plus hydroxide is formed. Instead, if we have, actually we'll go ahead and do an ice table on this. So if we had a 0.01, okay, so we could do an ice table on this, and we'll use 0.1 molar for ammonia to start with, and 0.10 minus X as the moles of ammonia at equilibrium, and X moles of ammonium and hydroxide. So Kb is 1.8 times 10 to the minus 5, X squared divided by 0.10 minus X. 0.10 divided by 1.8 times 10 to the minus 5 is greater than 100. So it's okay to drop that X, which makes life good. We have here X is equal to the square root of 0.10 times 1.8, 10 to the minus 5. X is equal to the hydroxide concentration, and that's 1.34 times 10 to the minus 3. POH equals 2.87, and pH equals 11.13. So it's a basic solution, which is what you would expect. Working with methylamine, it's directly analogous, and all you're doing here, you can put the methyl anywhere you want, by the way. So the only difference here is that you're dragging methyl around instead of hydrogen. So you have methyl ammonium, which has a positive charge, and then hydroxide. So methyl ammonium hydroxide is the product. And Kb for this one, 4.38, 10 to the minus 4. So if you did a similar ice table for 0.10 molar concentration, 0.10 minus x, x, and x, then you use 4.38, 10 to the minus 4 is equal to x squared over 0.10 minus x. X would be equal to the OH minus concentration, 6.62 times 10 to the minus 3 molar. POH equals 2.18, and pH would be equal to 11.82. So no difference between this reaction and the ammonia reaction. The ammonia reaction gave pH 11.13, so with the methyl group it's slightly more basic, meaning there's a little bit greater tendency to hydrolyze water with the presence of the methyl group. Otherwise, both solutions are basic. The chemistry is the same. You're just dragging the methyl group around. And again, the name of the compound formed would be methyl. So it would be a methyl ammonium hydroxide. Alright, I believe that's it for this talk.